Alright everyone, so with this video is going to kind of summarize what we need to see on this final test. So I am on page 27 in our notes, and this is just one of many examples. So I'm going to work through these two. I'll show you the answer key to a couple other pages as you try them on your own, and then as long as we can get you feeling confident on this, then you'll do great on the quiz. So you're going to have to draw Lewis dot structures on the quiz. So we have an H3O+. We'll talk about the plus in just a moment. So I'm going to put oxygen in the middle, and then I have 3 hydrogens. Okay. Now, hydrogens have 1 valence electron, and I've drawn the 1 valence electron that they've come with. Oxygen, on the other hand, has 6 valence electrons, and right now I've only drawn 1, 2, 3 of the 6. 2, 3, and so then I would go 4, 5, and then like a free radical, 6. But the plus means that we've lost a negative electron. So I can take that and we're gonna not have that negative electron. So let me redraw this so it's a little more clear. Oxygen in the middle with a lone pair, and then here's my hydrogens. Okay, so there's my H3O+. Whenever we have an ion, we'd put it in brackets, and then we put the charge on the outside. Okay. Step 2 is doing the electronegativity difference between the central atom and any outside or terminal atoms. So we're talking about oxygen and hydrogen. So we're going to look at your electronegativity table, and you'll get these on the quiz. And we're looking at oxygen, which has an electronegativity of 3.44, and hydrogen, which is 2.20. And I'm going to subtract those, and I'm just always going to do the bigger one minus the smaller one. So 3.44 minus 2.20. So 1.24. Okay. Just a reminder, and this will be on the board during the test. If you subtract these and you get a difference in electronegativity from 0 to 0.4, we would call that non-polar covalent. If you subtract them and you get a difference from 0.4 to 1.7, like we see right here, then that would be a polar covalent bond. Larger than that, we call it ionic. So all 3 of these bonds are polar covalent bonds because it falls between 0.4 and 1.7. Okay. I'm going to have you draw these dipole arrows whenever it's a polar covalent bond. So a reminder, dipole arrows point at the atom that's more electronegative. And oxygen is more electronegative than hydrogen is. So this bond would have an arrow, and it's like pointing at the oxygen because it's more electronegative. Same with this bond, and same with this bond. Okay. All right. Now we need to determine the AXE. So reminder, A means a central atom. So there is a central atom, so I'm going to say A. X is outside atoms, and there are 3 outside atoms, so it's going to be an X3. And E is lone pairs on the center atom. Okay, specifically lone pairs on the center, not on the outside atoms. So this this center atom has 1 lone pair, so it's just going to be E, like that. Okay. On the quiz, I'm not going to say Vesper shape, I'm going to say molecular shape. So let's think about this for a second, and you're going to get your yellow sheet, but we have 3 bonded atoms and 1 lone pair. Okay, so I have, and look at the top, bonded atoms, lone pairs. So I have 3 bonded atoms and 1 lone pair. So when we add those together, that would be 4 electron domains. The electron geometry is tetrahedral, but the molecular shape is trigonal pyramidal. And then there's my 3D shape. Okay, so trigonal pyramidal. and then I'm going to draw that 3D shape. You'll also have the model kit available to you, so if you want to, you can absolutely build it as well to help you with this. So here's the 3 bonded atoms. And here's the lone pair that's like right there, okay? And so here's the plane of our paper. So these 3 are the plane of the paper. There's a lone pair coming out of the paper towards us, and then there's an atom going into the paper away from us. And so it's like I have my center, I have these bonded atoms at an angle, and I got the one coming out of the paper, one going into the paper, lone pair, bonded atom. Okay, we need the dipole arrows though. If any polar bonds are present, draw the partial, guess what, I don't need you to worry about the partial charges, but I want you to do the dipole arrows. And remember, they're pointing towards the center, towards the oxygen. So we have pointing towards the oxygen, pointing towards the oxygen, and even this one is pointing towards the oxygen. Okay, do you see how these arrows do not cancel out? We definitely have asymmetry. This lone pair has completely thrown off the symmetry. Everything surrounding this oxygen was the same except for the lone pair. So when an entire molecule is symmetrical, this one's not. If it was symmetrical, it's a non-polar molecule. When it's asymmetrical, then it's a polar molecule. So just remember SNAP. So symmetry, everything around it is the same. The arrows are canceling. Then it's nonpolar. Asymmetry, especially lone pairs, really tend to throw off the symmetry. Not 100% of the time, but a good majority of the time. So when it's asymmetrical, it's polar. So this is a polar molecule. Alrighty, let's do one more together. So I have phosphorus, 2 fluorines, and 3 chlorines. So I'm going to put my phosphorus right here. And I'm going to do, let's see, 3. Let's do, like, here's my chlorine, maybe chlorine. Chlorine, try to spread these out. I don't know, fluorine, fluorine. Okay. Actually, let's do the outside atoms first. Chlorine has 7 valence electrons, so let's draw those in. We've only drawn one of the 7, so 1, 2, 3, 4, 5, 6, 7. So we're going to do that for all the chlorines. Okay. Fluorine also has 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7. Same on the other one. Okay, now our center, phosphorus. Phosphorus has 5. Yep, 5. And how many have I drawn? 1, 2, 3, 4, 5. So I don't need to add any more. This is an expanded octet, but that's okay because all of the atoms have a formal charge of 0. Chlorine has 7 valence electrons and it's a sign 7, so 0. Fluorine has 7 valence electrons and it's a sign 7, so it has a formal charge of 0. So 0, 0, 0, 0, 0. Phosphorus has 5 valence electrons and it's assigned 5 valence electrons, so it also has a formal charge of 0. So this is an optimal Lewis dot structure. But we got to think about this electronegativity difference because we got 2 different kinds of bonds here. We got chlorine bonded to phosphorus and we have fluorine bonded to phosphorus. So we need to do both of these. Let's start with the chlorine and the phosphorus. So here's phosphorus 2.19, here's chlorine 3.16. And I'm always just going to do the bigger one minus the smaller one. So 3.16 minus 2.19. Okay. Subtract those. 0.97. Okay, so that falls in the polar range. So this is a polar covalent bond. Let's check the other one. Fluorine is more electronegative. Oh, so this will also be polar. 3.98 minus the phosphorus, 2.19. And we get 1.79. And everyone, this is a very polar bond. These are two nonmetals. Phosphorus is nonmetal, fluorine's a nonmetal, and so it can't be ionic. So even though it's showing really, really high, like where we'd normally characterize it as ionic, because they're both nonmetals, I would just call them very polar bonds. So that's a polar covalent bond. Alrighty. We have our AXE. So there's an A, there's a center, there's outside atoms. Oh, there's 5, so X5, and there's no lone pairs on the center. Great. Now, let's use our shape guide to figure out what shape this is. We have 5 bonded atoms with 0 lone pairs. 5 bonded atoms, 0 lone pairs. Oh, so the electron geometry and the molecular shape are both trigonal bipyramidal. And when I draw this 3D shape, I'm going to show that I have my center, bonded atom. We get this like T shape, and this is in your shape guide. And then a wedge to an atom, and a wedge to an atom. Okay, now if we build this, we're going to see something interesting. Let me see if I can get a different color to help show you. What if the fluorines are on exact opposite sides? So there's our 2 fluorines. So they would actually cancel out. Like they have dipole arrows pointing towards the fluorine, but those ones would cancel. And then we got 3 chlorines. But if the chlorines all surround the center in that triangle, they cancel as well, because all 3 of them around the center are symmetrical, are the same. And so then those dipoles can cancel as well. So this is such an interesting one, because even though we have different types of atoms in it, we have symmetry, not asymmetry. So the whole thing is a nonpolar molecule. Okay, now what I'm going to do is I'm going to turn to page 25 first. I want you to try it on your own, and now I'm going to put it on screen, and you can hit pause and you can see how you did. Okay, good. I'm going to do one more page. Let's look at page 22. So try 22 on your own. Hit pause, try it on your own. Then when you're ready, hit play, and then I'll put it up on the screen. You can check your work. Okay. Good job, everyone. If you have any questions, feel free to reach out or sign up for a study session, and then I'll see you all in class.